Welcome to Cosmic Sedation, your peaceful sanctuary for the night. Tonight's journey takes us through He Found the Center of the Universe. Wished he hadn't, a tale that will gently guide you into dreams. Don't forget to subscribe and like if you're enjoying this ride as much as we are. Drop a comment letting us know where you're tuning in from tonight and what time usually sends you off to sleep. As the stars align and the night deepens, let's begin our calm descent together. In the heart of a solar flare's fury, silence birthed the coordinates to cosmic radiation's deepest secret. A team of scientists at Harvard University found themselves staring not into the void, but directly at Sagittarius A, the supermassive black hole that sits at the center of our galaxy. This point, 26,000 light-years away from Earth, is a region where time itself bends under the weight of gravity so intense it warps space-time to its limits. As cosmic radiation bombards Sagittarius A, it triggers an extraordinary process. Particles spiral towards the black hole's accretion disk, heating up due to friction. The temperature near this disk can reach up to 1 billion Kelvin, a heat that could vaporize entire planets if they were anywhere near such proximity. To a human body, this environment is inconceivable. Even the briefest exposure would reduce it instantly to subatomic particles. Yet, for astronomers studying from Earth, this radiation provides critical clues about black holes and their behavior. Each photon escaping before being swallowed by the event horizon carries information back into space, allowing us to piece together the mysteries of these celestial behemoths. At the core of Sagittarius A, cosmic radiation interacts with matter in ways that defy our understanding of physics as we know it on Earth. Here, particles are not simply atoms or molecules. They are torn apart into their fundamental components by the extreme conditions. The density near this black hole reaches an astounding 4 × 10⁹ solar masses per cubic parsec. Imagine compressing a mass equivalent to billions of suns into an infinitesimally small space. This pressure is so immense that it reshapes not only matter, but also time, creating regions where even light struggles to escape. The gravity is so strong that the fabric of space-time curves beyond what our minds can easily grasp. Yet through careful observation and analysis, scientists have mapped these distortions with remarkable precision. The radiation emitted from Sagittarius A plays a crucial role in shaping its immediate environment. Gamma-ray bursts lasting less than 2 seconds release more energy than the sun will produce over its entire lifetime, a fleeting burst of power that illuminates the cosmos for brief moments. These gamma rays interact with surrounding gas clouds, ionizing and dispersing them. This process not only influences star formation, but also helps regulate the overall structure of our galaxy. In a sense, this radiation acts as both sculptor and destroyer, continually reshaping the Milky Way from its center outward. It is a cosmic dance that has been playing out for over 13.6 billion years, since long before Earth existed. One might wonder how such extreme conditions could exist in our universe without affecting us here on Earth. The answer lies in distance and time dilation effects. At the galactic center, where Sagittarius A resides, light takes approximately 26,000 years to reach us, a journey that stretches across vast tracts of space. By the time any disturbance from these extreme conditions reaches our solar system, it is profoundly altered by the intervening epochs and distances. Moreover, the strong gravitational field near the black hole causes significant time dilation. For every second experienced in the vicinity of Sagittarius A, thousands or millions pass elsewhere. This means that even if something catastrophic were to happen at its core, we would not see it for millennia. While cosmic radiation shapes Sagittarius A and its immediate surroundings, this region also holds clues about our universe's origins and future. The cosmic microwave background radiation discovered by Penzias and Wilson in 1964 provides evidence that the cosmos began as a hot, dense point, a singularity from which everything emerged. Understanding how such extreme conditions influence black holes helps us piece together the story of the universe itself. In billions of years, Sagittarius A may continue to grow, eventually merging with nearby galaxies' supermassive black holes in grand cosmic collisions that will rewrite the structure of our galaxy and beyond. Yet, for now, it remains a source of mystery and wonder, constantly revealing new insights into the fabric of reality. A billion years ago, the center of our galaxy was not a black hole, but an embryonic cloud of gas and dust, spanning millions of kilometers in diameter, a nebula far less dense than today's interstellar space. This ancient nebula contained about 1 million solar masses, slowly drifting through the cosmos without any gravitational anchor to draw it together. In this primordial state, temperatures hovered around -230 degrees Celsius, with particles moving freely under low-pressure conditions. If you were to place a human there, your body would expand uncontrollably due to the lack of atmospheric resistance, but you wouldn't freeze instantly. The cosmic microwave background radiation from the Big Bang still permeated this nascent structure, offering a faint echo of the universe's birth. This cloud of gas and dust was already several billion years old, having formed after countless cycles of star birth and death throughout the cosmos. Imagine if Earth were a grain of sand on an immense beach, then our galaxy would be akin to an entire continent. Yet even within this vast scale, the center of our Milky Way was just beginning to stir with gravitational forces that would eventually lead to the formation of Sagittarius A, the nebula's glow stretched across light years. While nearby stars were still young and vibrant, their nuclear furnaces just ignited. To an observer on Earth at that time, it might have appeared as a vast, diffuse cloud in the night sky, a far cry from the complex structure we observe today. Over millions of years, the nebula's core began to contract due to its own gravity, drawing matter inward with increasing intensity. This process took place over an extended period, during which the density at the center increased exponentially. When this concentration reached a critical point, the conditions were ripe for the formation of a supermassive black hole. Sagittarius A, the transformation was not immediate, but gradual, with temperatures reaching upwards of 10 million Kelvin as fusion reactions sparked within collapsing clouds of gas. This stellar birth process is similar to what we see today in distant galaxies, each one a testament to the universal laws governing gravity and thermodynamics. Today, Sagittarius A sits at the heart of our galaxy, its event horizon casting an invisible shadow on space itself. However, this black hole is not alone. It coexists with millions of stars that orbit it in complex gravitational dances, each star contributing to the dynamic structure of our galaxy. The supermassive black hole's influence extends far beyond just its immediate surroundings. Its gravity shapes entire regions within the Milky Way. This interplay between stellar bodies and the central black hole has been happening for 13.6 billion years, sculpting a galactic landscape that is both ancient and ever-changing. Every second, light travels over 20,000 kilometers from our Sun to the center of the galaxy, yet it takes us 260,000 years to perceive this journey through time. Considering the vastness of cosmic time, humanity's brief existence becomes even more remarkable. While we have only been aware of Sagittarius A for a fraction of its history, our understanding of these celestial phenomena has expanded dramatically in recent decades. The transformation from nebula to supermassive black hole encapsulates not just the life cycle of our galaxy, but also the evolution of scientific thought. As we continue to explore and learn about this distant yet connected core, we uncover more about ourselves and our place within the universe. In the heart of our galaxy lies Sagittarius A, a supermassive black hole whose gravitational pull warps time in ways that baffle comprehension. For an observer near its event horizon, every second stretches into what seems like centuries due to extreme time dilation effects. This region is so dense that space-time itself curves dramatically, distorting the very fabric of reality. Imagine standing within a few light minutes of Sagittarius A time would stretch out impossibly long for you while racing forward outside your frame of reference. Each photon attempting to escape this zone carries with it a history warped by these extreme conditions. From our distant viewpoint, however, nothing seems amiss. Such is the deceptive nature of space-time anomalies. The black hole's event horizon marks the point beyond, which not even light can break free, ensuring that time for those trapped inside will never align with our understanding. The cosmic microwave background radiation reveals that our universe was once confined within an infinitely dense state known as the singularity. This initial point of infinite density and temperature contrasts starkly with Sagittarius A, where matter clumps but cannot escape its own gravity's grip. Near this black hole, temperatures can soar to 1 billion degrees Kelvin due to friction within the accretion disk, tearing apart atoms and molecules in a process that defies normal matter. This extreme heat also serves as a crucible for nuclear fusion, creating new elements that eventually seed future stars. As our galaxy rotates around this central point, each galactic year lasts approximately 250 million Earth years. This vast cycle is but a mere blink compared to Sagittarius A's age. It has existed for billions upon billions of years, far longer than life has existed on our planet. In contrast, the singularity from which our universe emerged was an infinitesimal fraction of a second in duration, yet its influence shaped cosmic inflation over 13.8 billion years. Near the event horizon of Sagittarius A, temperatures climb to 1 billion degrees Kelvin due to friction within the accretion disk. This extreme heat tears apart atoms and molecules, preventing any form of normal matter from existing as we know it. Yet, this inferno also serves a critical role in creating new elements through nuclear fusion processes, contributing to the periodic table that underpins our chemistry and biology. It's paradoxical how destruction here fuels creation elsewhere. Gamma-ray bursts observed near supermassive black holes like Sagittarius A release more energy than the Sun will emit over its entire lifetime, yet they last mere seconds from a human perspective. Time dilation effects ensure that for objects closer to Sagittarius A, time moves so slowly it is almost halted. This warping of time creates an illusion where distant stars and galaxies race past in fleeting glimpses, while our galaxy completes its rotation around the black hole at a glacial pace. The density near Sagittarius A can reach up to 4 billion solar masses per cubic parsec, creating extreme gravitational forces that disrupt atomic structures. This environment is so hostile that matter cannot exist in its normal state. Yet, this region also plays host to some of the universe's most energetic processes, including powerful jets of plasma ejected from Sagittarius A. These jets travel at near-light speeds and interact with surrounding clouds, creating shockwaves that accelerate particles to incredible energies. Despite these extreme conditions, the black hole's magnetic field can sometimes weaken, allowing brief windows for matter to escape in spectacular outbursts. The age of our galaxy is estimated at 13.6 billion years, making it one of the oldest in the known universe. In contrast, the supermassive black hole at its center has existed for a fraction of this time, only several hundred million years. Yet, its influence on the surrounding space and matter is profound, shaping the environment in ways that affect star formation and the distribution of elements throughout the galaxy. This demonstrates how even relatively young cosmic entities can have an outsized impact on their surroundings. Neutron stars near Sagittarius A emit powerful bursts of gamma radiation, releasing more energy than the Sun will emit over its entire lifetime. Yet these events last mere seconds from a human perspective. Time dilation effects ensure that for objects closer to Sagittarius A, time moves so slowly it is almost halted. This warping of time creates an illusion where distant stars and galaxies race past in fleeting glimpses, while our galaxy completes its rotation around the black hole at a glacial pace. In a region where temperatures soar to unimaginable heights, reaching as high as 1 billion Kelvin near Sagittarius A, there exists an enigmatic anomaly, a cold spot that defies all thermal expectations. This peculiar area is cooler by several thousand degrees compared to its immediate surroundings within the supermassive black hole's accretion disk. Here, matter orbits at speeds exceeding half the speed of light under immense gravitational influence. Contrary to what one might intuitively expect in such an extreme environment, this cold spot behaves as if it's disconnected from the surrounding heat dynamics. Theories suggest that intense magnetic fields may be responsible for channeling energy away from specific regions, thus cooling them down. This phenomenon is reminiscent of how Earth's upper atmosphere can become unexpectedly cooler due to solar-wind interactions, even though space itself seems devoid of such phenomena. The cold spot near Sagittarius A exists within a complex network of magnetic fields that extend across vast scales, spanning hundreds of light years. These fields twist and coil around each other like immense ropes, playing a crucial role in the dynamics of matter accretion onto supermassive black holes. The scale at which these interactions occur defies easy comprehension. For instance, the magnetic field strength near Sagittarius A can reach up to 10 billion Tesla, far beyond what we can generate on Earth with our most powerful magnets. This intensity suggests that magnetic fields might be more influential in shaping local environments than previously thought. Scientists propose that this cold spot could offer insights into how black holes influence their environments over time. It's a paradoxical reminder that even in systems as extreme and inhospitable as those near supermassive black holes, localized conditions can vary drastically. In the context of the Milky Way's life cycle, which spans 13.8 billion years, this cold spot represents just one small yet significant feature among many. Understanding this cold spot might also provide clues about the early universe's conditions when similar processes occurred around nascent supermassive black holes formed during galaxy mergers. The scale at which these cosmic events take place is staggering. These black holes could have influenced entire galactic clusters, shaping their evolution over billions of years. In contrast to this immense scale, our current methods for observing such phenomena are still limited by the constraints of time and distance. Telescopes can only capture light that has traveled millions or even billions of years to reach us, making real-time observations impossible. Interestingly, while temperatures near Sagittarius A can reach an astonishing billion Kelvin due to friction in its accretion disk, the cold spot remains anomalously cool. This temperature discrepancy is significant, equivalent to a difference of thousands of degrees across mere light hours within this extreme environment. The implications of such thermal variation suggest that magnetic fields play a far more dynamic role than previously thought, potentially affecting not only heat distribution, but also the flow and behavior of matter in these systems. Moreover, the cold spot's existence raises questions about how stable such anomalies might be over cosmic timescales. Given that Sagittarius A has been accumulating mass for billions of years, it is remarkable that this cooling effect persists amidst such a hot, turbulent environment. This stability hints at an equilibrium maintained by complex interactions between magnetic fields and accretion dynamics, offering scientists invaluable data points to refine their understanding of these processes on both local and galactic scales. The cold spot near Sagittarius A is not just a thermal anomaly. It's a window into the intricate physics that govern the universe's most extreme environments. As matter spirals toward the black hole, its path is influenced by magnetic fields that twist and untwist like cosmic ribbons. These interactions create patterns so complex that they could potentially be used to map the structure of the black hole's magnetic field in unprecedented detail. This mapping capability could provide critical insights into how energy is distributed within these systems, offering a clearer picture of the forces shaping our galaxy's center. In contrast to the cold spot at Sagittarius A, consider the coldest place known on Earth, Antarctica's eastern plateau, where temperatures can drop below -89 degrees Celsius. This terrestrial record pales in comparison to the temperature variations near a supermassive black hole's event horizon. The paradox here lies not only in the extreme thermal differences, but also in the scale of these phenomena. While scientists on Earth study such anomalies from a safe distance, cosmic events unfold at speeds and scales that challenge our ability to fully comprehend them. The cold spot near Sagittarius A is a testament to the unpredictable nature of physics in extreme environments. As matter accretes onto the black hole, it does so in a manner that defies simple thermal models. This suggests that there are still many unknowns in our understanding of how such systems operate. The magnetic fields involved may be key players in this process, guiding not just temperature distribution, but also the flow and behavior of matter near the event horizon. In the grand scheme of the universe's history, the cold spot at Sagittarius A is a fleeting anomaly within an enduring structure, the supermassive black hole that has been accumulating mass for billions of years. This brief thermal disruption provides scientists with a unique opportunity to study how magnetic fields and accretion processes interact in environments far removed from our everyday experience. Each observation brings us closer to understanding the complex interplay between these forces, offering insights into the birth and evolution of galaxies like our own. Standing at the center of the Milky Way, one would confront the formidable gravitational forces exerted by Sagittarius A, a supermassive black hole with an event horizon that marks the boundary where even light cannot escape. The human body, unprepared for such extremes, would begin to experience these forces immediately upon arrival. Each step closer to the singularity would feel like a journey across cosmic epochs. Gravity at this point distorts time so profoundly that every second experienced by a distant observer might seem like an eternity for someone near the event horizon. This temporal disparity is akin to the effect observed in high-gravity environments on Earth, but magnified beyond comprehension. The immense pressure and density here, reaching 4 billion solar masses per cubic parsec, would compress and disrupt atomic structures within a human body. Normal biological functions cease as molecules are torn apart, leaving behind subatomic particles in free fall toward the singularity. This disintegration underscores how matter behaves under such extreme conditions, unlike anything encountered on Earth. The sheer force would elongate the spine and stretch every cell along the axis toward the black hole's core, a process akin to what astronauts experience during high-gravity training, but amplified to an inconceivably severe degree. Despite the lethal environment near Sagittarius A, it's remarkable to consider that this region was once part of a much quieter, less dense nebula, perhaps similar to those found in star-forming regions today. Over billions of years, gravitational collapse concentrated matter here until it formed the supermassive black hole we see now. The sheer density and heat generated by accretion processes mean that this space is far from empty. Near Sagittarius A, gamma-ray bursts release more energy than the Sun will in its entire lifetime. These brief, intense flashes of radiation could sterilize any surrounding region of life as we know it. Imagine a human body at the event horizon of Sagittarius A here. Light cannot escape, sound has no medium to travel through, and time itself ceases to have any meaning for distant observers. In this final moment, before crossing the boundary into the black hole's interior, one would witness an eerie silence, broken only by the relentless pull of gravity that drags every atom inward toward a point where all known physics break down. The extreme environment near Sagittarius A is not just lethal, but also pivotal to understanding cosmic processes on the largest scales. Gamma-ray bursts from supermassive black holes like Sagittarius A have been observed to last for less than 2 seconds and release energy equivalent to 1044 joules. This immense burst of radiation can ionize nearby gases, potentially triggering star formation in surrounding regions. Thus, while these events are destructive on a local scale, they also play a crucial role in cosmic evolution by influencing the distribution of matter and energy throughout galaxies. The cosmic microwave background radiation discovered by Penzias and Wilson in 1964 provides evidence that our universe was once a hot, dense point. This discovery underscores how the extreme conditions near Sagittarius A are not unique, but part of a broader cosmic narrative. The universe began as an incredibly small, dense entity, and processes like those at play near supermassive black holes continue to shape it today. Understanding these phenomena helps us grasp the intricate dance of forces that govern the cosmos. At the center of our galaxy, Sagittarius A is not just a black hole. It's a site where matter creation defies conventional wisdom. Here, in the heart of the Milky Way, the extreme conditions near this supermassive black hole allow for atomic interactions that create matter from what appears to be nothingness itself. The temperatures here reach up to 1 billion Kelvin, surpassing even the hottest stars. This environment is so hostile it disrupts normal atomic structures, yet it's precisely these disruptions that enable unique particle formation. Within this region, space and time are warped beyond recognition. Photons struggle to escape the gravitational pull, creating a zone where light itself can't break free. The event horizon marks this boundary, but within it, something extraordinary happens. Particles emerge from the quantum vacuum through processes like Hawking radiation. This phenomenon suggests that matter creation is not just a cosmic accident, but an intrinsic property of extreme gravitational fields. In our universe's infancy, similar conditions may have facilitated the birth of galaxies and stars. The density near Sagittarius A reaches up to 4 billion solar masses per cubic parsec, a concentration unmatched elsewhere in the cosmos. This extraordinary pressure forces atoms into states that would otherwise be impossible. Imagine if you could compress all the matter on Earth, about 5.972 times 10^24 kilograms, into a volume no larger than your thumbnail. This is akin to what happens here. The sheer density alters the fundamental physics, leading to a realm where particles are born and die in rapid succession. These fleeting entities contribute to a cosmic soup of quantum fluctuations, continuously creating new forms of matter. These atomic interactions at Sagittarius A also connect us deeply with our own origins. Every atom in your body, including the iron in your blood, was once part of this primordial process. Stars that long since died scattered their ashes across space, eventually coalescing into planets like Earth. The matter creation near the black hole's event horizon is a direct continuation of this cosmic cycle, linking the distant past with our present existence. It's humbling to realize that we are made from star stuff, forged in extreme conditions similar to those at the center of galaxies. At Sagittarius A, the density and pressure are so immense that they create a region where particles can exist in multiple states simultaneously, a phenomenon known as quantum superposition. This bizarre state allows matter to behave both like particles and waves, challenging our understanding of reality itself. In this environment, the very rules of physics seem to bend, offering insights into how the universe might have behaved during its earliest moments. At this central nexus, time behaves peculiarly. For observers far away, time slows down dramatically near Sagittarius A. This effect is so pronounced that it would take an infinite amount of proper time for any object to reach or pass through the singularity. Yet from within such extreme conditions, we can observe a process where matter emerges spontaneously. In this sense, the black hole acts as both a destroyer and creator. The paradox lies in the fact that while nothing escapes once past the event horizon, an active creation of particles occurs at the boundary, illustrating how even destruction can birth new beginnings. As these atomic interactions continue to shape the universe at its core, they hint at deeper questions about the nature of reality itself. If matter can be created from seemingly empty space under such extreme conditions, what does that say about the fabric of our cosmos? The processes near Sagittarius A challenge our understanding of physics and push the boundaries of human knowledge. This central nexus is a laboratory for the most fundamental forces in existence, revealing how the universe constructs itself out of its own destruction. At the center of the Milky Way lies Sagittarius A, a supermassive black hole with a mass equivalent to about 4 million suns. This celestial giant resides approximately 26,000 light-years from Earth, anchoring our galaxy's structure and influencing its evolution in profound ways. The extreme gravitational forces here warp space-time, affecting the orbits of nearby stars and gas clouds. Sagittarius A is not just a point where matter disappears into darkness. It acts as an energetic engine that drives much of the activity within our galaxy. As it accretes surrounding material, friction between particles causes temperatures to soar to 1 billion Kelvin near its event horizon. This intense heat and pressure disrupt atomic structures, turning matter into plasma. Simultaneously, powerful jets are expelled from the poles of this black hole at nearly the speed of light, shaping star formation across vast distances. Remarkably, despite being invisible to direct observation, Sagittarius A leaves unmistakable traces in its environment. These include high-energy radiation and the peculiar orbits of nearby stars, which move in complex patterns due to the immense gravitational pull. The influence of this black hole extends far beyond its immediate vicinity, affecting star formation and structure throughout our galaxy. The density near Sagittarius A can reach an astounding 4 × 10⁹ solar masses per cubic parsec, creating conditions where normal matter cannot exist as we know it. Yet, in this extreme environment, the black hole's gravitational influence shapes the very fabric of space-time, bending light and distorting time for nearby objects. This dynamic interplay between matter and energy underscores the paradoxical nature of Sagittarius A, a source of both immense destruction and cosmic creation. Looking back over billions of years, we can trace how Sagittarius A has been a central player in the Milky Way's development. From its origins as a dense cloud of gas to its current state as an active supermassive black hole, it has continuously shaped the galaxy's structure and influenced star formation. This core region is not merely a center, but a heart pumping life into the galaxy's vast network of stellar nurseries and dark, star-filled arms. In the distant future, Sagittarius A will continue to evolve through accretion and potential mergers with other black holes. Its influence on our galaxy's structure will persist for billions more years, guiding the formation of stars and shaping the cosmic landscape around it. This central engine not only propels the Milky Way's evolution, but also provides insights into the fundamental processes that govern galaxies across the universe. At Sagittarius A, matter does not exist in its ordinary state due to extreme temperatures and pressures. Instead, particles are torn apart, their atomic structures disrupted by forces far beyond human comprehension. Yet, this environment is crucial for understanding how stars form and evolve throughout the galaxy. The energy released from the black hole's accretion disk powers cosmic phenomena that extend far beyond our immediate view. Gamma-ray bursts from Sagittarius A last less than 2 seconds, but release more energy than the Sun will in its entire lifetime. These brief, intense events are a testament to the immense power contained within this region. The radiation emitted by these bursts can travel across 10 billion light-years, affecting distant galaxies and potentially influencing their formation. This underscores how processes at the heart of our galaxy have far-reaching consequences for cosmic structures. The age of the Milky Way is estimated at about 13.8 billion years, making it one of the oldest galaxies in the universe. Sagittarius A, with its supermassive black hole, has been central to this long history. Over billions of years, it has grown through accretion and mergers, shaping the galaxy's structure and influencing star formation. This ancient core continues to evolve, playing a pivotal role in the Milky Way's ongoing development. In contrast to our relatively stable solar system, the orbits of stars around Sagittarius A are anything but simple. These stars move in complex paths determined by the immense gravitational pull of the black hole, creating a dynamic and ever-changing environment. The sheer scale of these interactions highlights the complexity hidden at the heart of galaxies, where processes occur on scales that dwarf our everyday experiences. Looking forward, Sagittarius A will continue to grow through accretion and mergers with other black holes, potentially shaping the future structure of our galaxy for billions more years. The cosmic microwave background radiation, discovered by Penzias and Wilson in 1964, provides evidence that our universe was once a hot, dense point. This discovery reveals that Sagittarius A is not an isolated phenomenon, but part of a larger cosmic narrative. The energy released from black holes like this one contributes to the overall structure and evolution of the universe. Understanding these processes helps us grasp how galaxies form and evolve over time. However, surprisingly, the radiation patterns in the cosmic microwave background show slight irregularities that hint at quantum fluctuations during the Big Bang, suggesting a level of unpredictability even in the early universe. Gamma-ray bursts from supermassive black holes, such as Sagittarius A, are among the most energetic events in the universe. These brief, intense flashes of radiation last less than 2 seconds, but can outshine entire galaxies for short periods. This phenomenon highlights the extreme nature of these cosmic engines and their profound impact on the surrounding environment. The energy from these bursts can travel across 10 billion light-years, influencing distant galaxies and potentially shaping their formation. In the core of our galaxy, Sagittarius A is a place where physics behaves in ways that challenge human understanding. At its heart lies an object so dense it defies comprehension, a singularity compressed to a point with infinite density. This is where matter reaches its most extreme state, yet just beyond this infinitesimal point lies the void of space, empty and devoid of mass. The contrast between these extremes creates conditions that are both alien and pivotal in shaping our universe. Near the event horizon of Sagittarius A, temperatures can climb to 1 billion Kelvin due to friction within an accretion disk composed of matter spiraling inward. Yet this scorching environment contrasts starkly with the vast coldness just outside, where temperatures plummet close to absolute zero. This peculiar boundary is a testament to how gravity warps space-time, creating zones that are both incredibly hot and shockingly cold in different directions around the black hole's perimeter. The extreme density at its core distorts time itself. For objects closer to this point, time effectively slows down relative to distant observers, as if being swallowed into a temporal abyss. At the edge of Sagittarius A, where infinite density meets empty void, light behaves unpredictably. Photons that graze close to the event horizon are stretched and distorted by gravitational forces, an effect known as gravitational lensing. This phenomenon can bend and magnify images of distant stars or galaxies behind it, revealing a cosmic kaleidoscope visible only in this unique environment. The energy levels here are so intense that gamma-ray bursts lasting less than 2 seconds release more energy than the sun will emit over its entire lifespan. This fleeting burst of radiation is a reminder of how transient and powerful these events truly are. The boundary layer around Sagittarius A acts as an interface between extremes, Where matter entering the black holes, gravitational well experiences incredible compression before vanishing into oblivion. Yet this area also serves as a crucible for new star formation elsewhere in the galaxy. As gas clouds approach the supermassive black hole, their interactions generate shockwaves that can trigger starbirth in adjacent regions of space. This paradoxical role highlights how destructive forces at one scale can be constructive on another, illustrating nature's intricate balance. The cosmic microwave background radiation, discovered accidentally by Penzias and Wilson in 1964, provides a clue about the universe's early state, a hot, dense point from which all matter expanded. This radiation is a remnant of the Big Bang, with a temperature of approximately 2.73 Kelvin today. It fills the universe uniformly and has been used to measure minute fluctuations that seeded galaxy formation. These tiny variations in density are key to understanding how galaxies formed over billions of years. At this boundary, where infinite density meets empty void, time dilation effects become pronounced. For an observer near Sagittarius A, every second feels like eternity due to extreme gravitational forces bending spacetime. Yet paradoxically, as one moves away from the event horizon, time appears to normalize again. This peculiar property of black holes illustrates how they serve as cosmic clocks that slow down relative to distant observers. The contrast between these extremes highlights the extraordinary nature of Sagittarius A, a place where physics stretches our understanding to its limits. At a distance of 26,000 light-years from Earth, Sagittarius A is not merely a point in space, but a gravitational nexus where matter and energy converge in profound ways. The supermassive black hole at our galaxy's heart exerts an influence that reaches far beyond its immediate vicinity, shaping the very fabric of spacetime around it. Surrounding this core are regions filled with dark energy, a mysterious force comprising about 70% of the cosmos, pushing galaxies apart with invisible hands. Dark energy makes up about 70% of the cosmos, yet we know little more than its effects on cosmic expansion. It is not matter or light, but something far stranger. Its presence can be inferred only from how it affects distant objects moving away from us faster than they should. This unseen force acts like a constant pressure, counteracting gravity across galactic scales. In the context of Sagittarius A, dark energy underscores the paradoxical balance between attraction and repulsion that governs our universe. Interestingly, recent studies suggest that dark energy may also influence the spin rate of black holes, potentially slowing them down over time. The region around Sagittarius A is also teeming with particles we do not yet understand, neither ordinary matter nor dark matter, nor any known form of radiation. These unknown entities may contribute to the enigmatic properties of the galactic center, including its unique gravitational landscape. The temperature near the event horizon can reach up to 1 billion Kelvin due to friction within the accretion disk. Yet this extreme heat is overshadowed by the cold void just beyond it, an area where particles move at nearly light speed without generating significant thermal radiation. While Sagittarius A dominates our immediate view of the galactic center, the surrounding space contains a system of black holes and neutron stars orbiting in intricate patterns. These objects are influenced by the supermassive black hole's gravitational well. The density near this point can reach up to 4 billion solar masses per cubic parsec, creating conditions so extreme that matter cannot exist as we know it. Here, atoms are torn apart into their constituent particles and beyond, forming a plasma of protons, neutrons, electrons, and more exotic quarks. Farther away from the galactic core, dark energy's influence becomes more pronounced. This expansive force stretches space itself, pulling galaxies outward as if they were caught in an invisible web. The cosmic microwave background radiation discovered by Penzias and Wilson provides evidence of this expansion, revealing a universe that was once a hot, dense point. Yet, within the heart of our galaxy, Sagittarius A remains relatively stable despite its violent accretion processes and extreme conditions. It is a testament to the balance between gravitational attraction and cosmic repulsion. The age of the Milky Way, estimated at about 13.8 billion years, places it among the oldest galaxies in the universe. This longevity means that Sagittarius A has had ample time to accumulate mass through the accretion of gas, dust, and smaller black holes. The supermassive black hole's growth is not a smooth process. It experiences bursts of activity when matter falls into its accretion disk at high velocities. These periods are marked by intense radiation emissions that can be detected across vast distances in the electromagnetic spectrum. Notably, these gamma-ray bursts last for less than 2 seconds, but release more energy than the Sun will emit over its entire lifetime. At the center of our galaxy lies Sagittarius A, a supermassive black hole that marks the gravitational heart of the Milky Way. This cosmic giant is approximately 26,000 light-years from Earth and holds a mass equivalent to about 4 million suns. Near its event horizon, time behaves in ways that challenge conventional understanding, stretching out to what seems like eternity for any observer close enough. As matter spirals inward towards Sagittarius A, it forms an accretion disk where temperatures can reach up to 1 billion Kelvin due to the friction generated by colliding particles. Yet, paradoxically, there exists a cold spot near this supermassive black hole, defying thermal expectations and offering scientists a unique puzzle to solve. This anomaly suggests that even in such extreme conditions, unexpected phenomena can occur, hinting at processes yet unknown. At the center of our galaxy, time dilation effects become so pronounced that they effectively freeze time for objects near Sagittarius A for distant observers. This moment appears as a brief interruption in the flow of cosmic events. However, from the perspective of an object approaching the event horizon, each second stretches into what could be centuries or even millennia. This phenomenon underscores the vast difference between our perception of time and that experienced by objects near black holes. Within the ergosphere of Sagittarius A, a region just outside its event horizon, matter experiences intense gravitational forces, but can still orbit without being immediately consumed. Objects here are subjected to extreme tidal forces that stretch them in one direction while compressing them in another. This zone serves as a final stage before complete absorption into the black hole, where time's progression slows to an imperceptible crawl. Here, objects can theoretically extract energy from the black hole through a process known as the Penrose process, defying expectations of total absorption. The moment of cosmic stasis near Sagittarius A is not merely a theoretical concept, but also a consequence of our universe's fundamental laws of physics. Albert Einstein's theory of general relativity predicts that massive objects like black holes warp spacetime, leading to phenomena such as time dilation and the cessation of time progression at event horizons. This precise demonstration of Einstein's equations highlights both the complexity and elegance of these physical principles. For instance, near Sagittarius A, time slows down by a factor of 10⁶ for every meter closer to the event horizon. The heart of Sagittarius A is a region where particles are not only stretched by gravitational forces, but also experience a bizarre cooling effect due to blue-shifting radiation. In this area, temperatures near the accretion disk can reach up to 1 billion Kelvin, yet certain spots remain mysteriously cold. This paradoxical coexistence challenges our understanding of thermal dynamics in extreme environments and underscores how nature operates beyond human intuition. The temporary stasis near Sagittarius A represents both an end for some objects and a beginning for others, illustrating the intricate balance between destruction and creation within our galaxy's gravitational heart. The core of this supermassive black hole reaches up to 4 × 10⁹ solar masses per cubic parsec. This extreme compression creates conditions where matter can no longer exist in its normal state, disrupting atomic structures and leading to a realm where physics behaves unpredictably. The gravitational forces here are so intense that they warp spacetime itself, creating regions where light cannot escape. Near Sagittarius A, gamma-ray bursts have been observed lasting for less than 2 seconds, but releasing more energy than the Sun will in its entire lifetime. These brief, powerful events highlight the immense power contained within this region of space. The energy released during these bursts is equivalent to millions of supernovae exploding simultaneously, yet they occur so quickly that they are barely detectable. The cosmic microwave background radiation, discovered by Penzias and Wilson in 1964, provides evidence that our universe was once a hot, dense point. This discovery suggests that the conditions near Sagittarius A may offer insights into the early moments of the universe, where extreme temperatures and pressures were commonplace. The paradoxical cold spot near this supermassive black hole could be a relic from these primordial times, offering clues about the origins of our cosmos. In the vicinity of Sagittarius A, time itself becomes distorted in ways that are difficult to comprehend. For an observer approaching the event horizon, every second stretches into what seems like centuries due to extreme time dilation effects. This phenomenon means that while it might take a human only moments to reach the point of no return, from the perspective of someone far away, this journey could appear to last for eons. The age of the Milky Way is estimated at about 13.6 billion years, making it one of the oldest galaxies in the universe. Sagittarius A, having existed since the dawn of our galaxy, has witnessed countless cosmic events unfold over its long lifetime. It has seen stars form and die, planets coalesce, and civilizations rise and fall, yet it remains unchanged, a timeless sentinel at the heart of our galaxy. At the center of this supermassive black hole lies an object so dense it defies comprehension, a singularity compressed to a point with infinite density. This region is a place where conventional physics breaks down, and the very fabric of space-time becomes distorted beyond recognition. The paradoxical nature of this singularity challenges our understanding of reality itself, offering a glimpse into the limits of what we can know about the universe. In the heart of our galaxy, Sagittarius A, a supermassive black hole with a mass equivalent to about 4 million suns, exerts gravitational forces so intense that they influence quantum events on Earth in ways both subtle and profound. At its core, extreme temperatures reach up to 1 billion Kelvin due to accretion disk friction. Particles near this cosmic giant become entangled with their counterparts across vast distances, including here on Earth. Quantum entanglement means that the state of a particle can instantaneously influence its twin, even if they are light years apart. This phenomenon connects Sagittarius A not just to distant stars and galaxies, but also to microscopic events in our laboratories. Consider an electron orbiting close to Sagittarius A. Its quantum state is entangled with another electron that may have been created at the moment of the Big Bang, billions of years ago. When a cosmic event, such as a gamma-ray burst, occurs near the black hole's accretion disk, it can alter the spin or position of this distant electron. These minute changes ripple through space-time to influence experiments conducted in our most advanced laboratories. Scientists have designed sensitive instruments that can detect these quantum fluctuations caused by cosmic events at Sagittarius A. The effects are often minuscule but measurable, just enough to reveal a hidden connection between the galactic center and Earth's smallest particles. This link operates with an efficiency that defies human intuition, highlighting how deeply interconnected our universe truly is. The implications of this quantum entanglement reach far beyond scientific curiosity. It suggests that events at Sagittarius A can subtly affect the outcomes of experiments conducted in our laboratories, influencing probabilities in ways not fully understood yet. For instance, the behavior of electrons in semiconductors or nuclear particles in reactors might carry subtle imprints from distant cosmic phenomena. This connection between microscopic quantum events and the galactic heart underscores a fundamental truth. The universe is an intricate web of interdependencies. Each small event on Earth, no matter how inconsequential it may seem, can be influenced by processes occurring at the center of our galaxy, where temperatures reach unimaginable heights and time itself seems to stand still. Yet, despite this profound link, the quantum effects remain so delicate that they are only detectable with highly sophisticated instruments. The extreme density near Sagittarius A, reaching up to 4 × 10⁹ solar masses per cubic parsec, creates conditions where atomic structures can no longer exist in their normal state. This environment disrupts the very fabric of matter, leading to unique quantum phenomena that challenge our understanding of physics. These extreme conditions near the black hole's event horizon provide a laboratory for studying processes that are otherwise impossible on Earth. Gamma-ray bursts from supermassive black holes like Sagittarius A release more energy in less than 2 seconds than the Sun will emit over its entire lifetime. This brief but intense burst of radiation can influence particle interactions across distances up to 10,000 parsecs, including those affecting particles here on Earth. The sheer scale and intensity of these events highlight how seemingly local phenomena are interconnected with processes occurring light years away. The cosmic microwave background radiation discovered by Penzias and Wilson in 1964 provides evidence that our universe was once a hot, dense point. This discovery reveals that the universe began as an incredibly compact space where quantum fluctuations played a crucial role in shaping its structure. These early quantum events laid the foundation for the formation of galaxies, stars, and eventually life on Earth. However, recent studies suggest that some of these initial fluctuations may have been influenced by gravitational waves from supermassive black holes like Sagittarius A, creating subtle patterns in the cosmic microwave background radiation. The age of the Milky Way is estimated at about 13.6 billion years, making it one of the oldest galaxies in the universe. This long history means that Sagittarius A has been influencing our galaxy's evolution for billions of years. The gravitational forces exerted by this supermassive black hole have shaped not only the structure of the Milky Way, but also its dynamics and the distribution of matter within it. Understanding these connections helps us appreciate how events at the galactic center can influence microscopic quantum phenomena on Earth. This interplay between the vast cosmic scale and the infinitesimal quantum world underscores the intricate nature of our universe, where distant processes have tangible effects on local physics. As we continue to explore this relationship, we deepen our understanding of the fundamental principles that govern both the cosmos and the particles within it. In the center of our galaxy, Sagittarius A is a region where matter and energy are intertwined in ways that challenge our understanding of physics. The supermassive black hole's immense gravitational pull warps spacetime itself, creating conditions so extreme they defy human comprehension. At this point, the fabric of reality stretches and compresses, bending light paths and altering the flow of time around it. Were one to approach Sagittarius A, the stars would appear increasingly distorted, their light bending into swirling patterns as spacetime curves ever more sharply. Should the core of our galaxy become destabilized, it could ripple through cosmic scales, affecting not just nearby galaxies, but entire galactic clusters. Imagine a disturbance so powerful that it sends shockwaves across millions of light years, altering the gravitational balance between distant stars and black holes by shifting their orbits by up to 100 kilometers per second. This would be akin to dropping a pebble in a pond, but instead of ripples on water, we are seeing changes in the very structure of the universe. The implications extend far beyond our own galaxy's borders, touching the lives of countless celestial bodies that have never even seen our sun. At the heart of Sagittarius A lies an accretion disk, a swirling mass of matter spiraling towards the event horizon at incredible speeds. This disk generates temperatures reaching 1 billion Kelvin due to friction as particles collide and heat up under immense gravitational forces. The sheer energy output from such processes could potentially trigger gamma-ray bursts that release more energy than our sun will emit over its entire 13.8 billion-year lifespan. Yet, in this environment, life would not be conceivable. The conditions are too harsh for any form we understand to exist. As time progresses and the universe ages, Sagittarius A will continue to influence the fate of our galaxy. Over billions of years, it may merge with other black holes or consume surrounding stars, potentially creating even more massive singularities that alter galactic dynamics. These events could lead to a new era for the Milky Way, shaping its structure and evolution in ways we cannot yet predict. Meanwhile, distant observers would witness these changes unfold over unimaginable timescales, watching our galaxy transform from afar. The stability of Sagittarius A is crucial not only for the Milky Way, but also for the entire cosmos. Its role as a gravitational anchor ensures that stars maintain their orbits and that the delicate balance of forces within our galaxy remains intact. Any disruption could send ripples through space-time, affecting the very structure of the universe on scales far beyond what we can observe today. This interconnectedness is a reminder of how deeply entwined celestial bodies are in shaping cosmic landscapes over billions of years. Considering the future threats posed by destabilization at Sagittarius A, it becomes clear that small changes in this region could have profound consequences for the universe as a whole. The intricate dance of matter and energy around the supermassive black hole is constantly evolving, with each passing moment potentially setting new cosmic patterns into motion. These dynamics underscore the delicate balance between order and chaos in the cosmos, highlighting the fragility and resilience inherent in our understanding of space itself. Instruments designed to detect cosmic rays and dark matter operate at the periphery of human perception, translating invisible signals into data. These detectors are sensitive enough to pick up particles that have traveled across galaxies, some for billions of years. Each particle detected is a messenger from distant parts of the universe, carrying information about its journey and origin. For instance, cosmic rays can reveal the conditions in supernova remnants or near black holes, offering insights into extreme environments. One such instrument, the Alpha Magnetic Spectrometer, orbits Earth aboard the International Space Station. It detects cosmic rays with unprecedented precision, capturing particles like protons, electrons, and even antimatter that would otherwise pass through our planet undetected. These cosmic messengers are the result of high-energy collisions in distant regions, such as supernova explosions or the accretion disks surrounding black holes. The AMS has found an excess of positrons, suggesting a new source of these particles, potentially linked to dark matter interactions. This discovery hints at the presence of undiscovered physics beyond the standard model. In the vicinity of Sagittarius A, detectors would register a symphony of high-energy events due to the intense gravitational environment. Here, cosmic rays are accelerated to near-light speeds by magnetic fields and shockwaves generated as gas swirls into the black hole's accretion disk. The density of particles in this region is so extreme that it creates conditions where matter is continuously being torn apart and reformed under unimaginable pressures. Instruments like gamma-ray telescopes can detect these emissions, revealing specific energy signatures that indicate particle collisions at near-light speeds, providing insights into the chaotic processes near the event horizon. The detectors are not just passive observers. They actively sift through the stream of incoming particles, using magnetic fields and silicon trackers to differentiate between various types. For example, these instruments can tell the difference between an electron and a positron based on their charge and mass. This precision is crucial because it allows scientists to map cosmic phenomena with unprecedented accuracy. Each detected particle carries its own story, a tale of how the universe has shaped itself over billions of years. Instruments like the Fermi Gamma-ray Space Telescope have provided detailed maps of gamma-ray emissions, revealing the complex interactions near supermassive black holes. At the heart of Sagittarius A, temperatures can reach up to 1 billion Kelvin, a result of friction in the accretion disk as matter accelerates towards the black hole's event horizon. Instruments like X-ray telescopes are crucial here, as they detect high-energy emissions that would otherwise be invisible to human eyes. These instruments reveal not just what is present, but also how it moves and interacts. For instance, the detection of iron atoms near Sagittarius A indicates recent star formation or supernovae events in its vicinity. The presence of heavy elements like iron suggests a history of stellar evolution in this region. However, surprisingly, these regions can also host pockets of relatively cool gas, where temperatures drop to just tens of thousands of Kelvin, creating stable environments for molecular clouds and potential sites for future star formation. The data collected by these detectors challenges our understanding of fundamental physics. Dark matter remains elusive yet essential for explaining phenomena like galaxy rotations and gravitational lensing. Instruments designed to detect dark matter particles aim to solve this cosmic puzzle, offering insights into the invisible matter that makes up a significant portion of the universe's mass. For example, experiments like the Large Hadron Collider are searching for signs of dark matter interactions at particle collision sites. As we continue to refine these instruments, each new detection brings us closer to understanding the invisible architecture of our cosmos. In the heart of our galaxy, Sagittarius A is not just a supermassive black hole, but a gravitational nexus where dimensions intersect in ways that challenge human understanding. Here, space and time warp around an object so dense it defies comprehension, a singularity compressed to a point with infinite density. As you approach this cosmic center, the fabric of space-time becomes increasingly distorted, bending light and altering the path of nearby stars. The journey through these intersecting dimensions is one where familiar concepts of motion and direction dissolve. The temperature near Sagittarius A can reach up to 1 billion Kelvin due to friction within its accretion disk. This heat could melt atoms into plasma in mere moments if exposed directly. Yet just beyond this inferno lies a cold spot where temperatures plummet, a paradoxical anomaly that defies thermal expectations. The contrast between these extremes highlights the complexity of forces at play near the galactic center. For an observer moving through this region, time itself would stretch and compress unpredictably, with seconds feeling like centuries or collapsing into fleeting instants. As you move closer to Sagittarius A, the density increases dramatically, reaching up to 4 billion solar masses per cubic parsec. This extreme compression disrupts atomic structures, transforming matter into an exotic state known as neutronium, dense material found only near black holes and neutron stars. The sheer force of gravity here would tear apart any object, including atoms, leaving behind a substance so dense it challenges the limits of our understanding. Yet, amidst this chaos, there is order. The supermassive black hole's immense gravitational pull keeps the entire galactic disk in orbit, while regulating star formation and supernova explosions across its vast expanse. For instance, some stars near Sagittarius A rotate around their axes at speeds that exceed 10% of the speed of light, a counterintuitive observation given the extreme gravitational forces acting upon them. The journey through these intersecting dimensions reveals how intimately connected we are with the universe's most extreme environments. The iron in your blood was forged in stars that died before our sun existed, and much of it likely originated from supernovae explosions near the galactic center. These ancient stellar deaths contributed to the formation of new generations of stars and planets, including our own solar system. For example, approximately 2% of the iron atoms in your body were created in a specific Type Ia supernova explosion that occurred about 13 billion years ago, close to where Sagittarius A now resides. The supermassive black hole at the heart of our galaxy not only warps spacetime, but also influences the very structure of the Milky Way itself. Its gravitational pull keeps the entire galactic disk in orbit, while regulating star formation and supernova explosions across its vast expanse. In this way, Sagittarius A acts as a cosmic governor, ensuring that the galaxy maintains its delicate balance over billions of years. Yet, despite its influence, the black hole remains invisible to direct observation due to the extreme gravitational forces bending light beyond recognition. As you continue your journey through these intersecting dimensions, you encounter regions where time dilation effects become pronounced. For an observer near Sagittarius A, every second stretches into what seems like centuries due to extreme time dilation effects. This phenomenon is a stark reminder of how our perception of time can be altered by the forces at play in this region. The journey through these intersecting dimensions reveals unexpected patterns. Light from distant stars appears as streaks and loops, defying conventional notions of linear travel. In the heart of our galaxy, Sagittarius A is a region where pressure defies common expectations. This supermassive black hole, with a mass equivalent to about 4 million suns, resides approximately 26,000 light-years from Earth. Near its event horizon, the vacuum density reaches up to 4 × 10⁹ solar masses per cubic parsec, creating an environment that challenges our understanding of pressure and emptiness. At this point, matter cannot exist in its normal state due to extreme temperatures and pressures that disrupt atomic structures. Gamma-ray bursts from supermassive black holes like Sagittarius A have been observed to last for less than 2 seconds, but release more energy than the Sun will emit over its entire lifespan. These brief, intense events highlight how matter is transformed under such extreme conditions, offering a glimpse into the efficiency of cosmic processes at play within these regions. The radiation emitted during these bursts can travel across vast distances, reaching Earth and providing valuable data for astronomers. At the core of our galaxy, Sagittarius A influences time itself through powerful gravitational forces. The strong curvature of spacetime causes light to orbit in a photon sphere, a boundary where photons travel around the black hole due to intense gravitational attraction. This phenomenon demonstrates how pressure can influence even the behavior of light and spacetime. For an observer near this region, every second stretches into what seems like centuries due to extreme time dilation effects. Additionally, objects approaching the event horizon experience a dramatic increase in their mass as they accelerate towards the black hole, making them appear heavier than they actually are. The cosmic microwave background radiation discovered by Penzias and Wilson provides evidence that our universe began as a hot, dense point. This initial state contrasts with the cold vacuum near Sagittarius A, where temperatures spike due to accretion disk friction. The coexistence of such extreme conditions challenges conventional notions of temperature distribution in space. These findings suggest that the universe's early stages were far more chaotic and energetic than what we observe today. In this extreme environment, matter behaves differently from its normal state on Earth. Atomic structures are disrupted by intense pressures and temperatures, leading to unique phenomena like the creation of particles from energy itself. This process underscores how pressure can influence fundamental physical processes, even at scales beyond human comprehension. The iron in your blood was forged in a star that died before our sun existed, illustrating the cosmic recycling of elements. The supermassive black hole's immense gravitational pull warps spacetime itself, creating conditions so extreme they defy easy explanation. Near Sagittarius A, light cannot escape beyond the event horizon because the gravitational pull is too strong for photons to overcome. This boundary marks a point of no return where time and space are distorted in ways that challenge human understanding. Yet these distortions provide crucial insights into the nature of gravity and the fabric of reality itself. The vacuum near Sagittarius A is not merely empty space, but a realm where density reaches unprecedented levels. Despite being a vacuum, this region contains more mass than can be found in entire galaxies. This paradoxical situation challenges our intuitive understanding of what constitutes emptiness and fullness. The pressure here is so intense that it warps the very fabric of space-time, bending light paths and altering the flow of time itself. Such conditions are far removed from the gentle atmospheric pressures we experience on Earth. Gamma-ray bursts from supermassive black holes like Sagittarius A have been observed to last for less than 2 seconds, but release more energy than the Sun will emit over its entire lifespan. These brief, intense events highlight how matter is transformed under such extreme conditions, offering a glimpse into the efficiency of cosmic processes at play within these regions. The radiation emitted during these bursts can travel across vast distances, reaching Earth and providing valuable data for astronomers. The supermassive black hole's immense gravitational pull warps spacetime itself, creating conditions so extreme they defy easy explanation. Near Sagittarius A, light cannot escape beyond the event horizon because the gravitational pull is too strong for photons to overcome. This boundary marks a point of no return where time and space are distorted in ways that challenge human understanding. Yet these distortions provide crucial insights into the nature of gravity and the fabric of reality itself. At the core of our galaxy, Sagittarius A influences time itself through powerful gravitational forces. The strong curvature of spacetime causes light to orbit in a photon sphere, a boundary where photons. At the center of our galaxy lies Sagittarius A, a supermassive black hole with a mass equivalent to about 4 million suns. This cosmic giant resides approximately 26,000 light-years from Earth and holds a pivotal role in shaping the universe around it. Its gravitational pull warps spacetime, creating conditions that influence black hole formation up to 10 kiloparsecs away. The extreme density near Sagittarius A can reach up to 4 times 10 to the 9th solar masses per cubic parsec, a pressure so intense it disrupts atomic structures and causes matter to behave in ways that challenge conventional understanding. The temperature near Sagittarius A can reach up to 1 billion Kelvin due to accretion disk friction, a heat so intense it would instantly vaporize any material we know, including iron. Yet within this inferno, there exists a cold spot, an anomaly where temperatures dip below the surrounding extreme levels. This paradox highlights complex interactions between matter and energy near the black hole, illustrating how even in such an extreme environment, unexpected phenomena can occur. For instance, the cold spot's existence suggests that magnetic fields could play a role in cooling regions of intense heat, potentially influencing the formation of smaller black holes nearby. Our galaxy is estimated to be about 13.8 billion years old, making Sagittarius A one of the oldest known supermassive black holes in the universe. Its influence extends far beyond its immediate vicinity, guiding the formation of stars and black holes throughout the Milky Way's history. The gravitational forces exerted by this central object have played a crucial role in determining our galaxy's structure and evolution. This ancient black hole has been influencing cosmic processes for nearly as long as the universe itself has existed. As Sagittarius A continues to rotate, it distorts spacetime in ways that create unique pathways for matter to form into stars and eventually collapse into black holes. These processes occur under conditions of extreme density and temperature, reaching up to 10 times 10 to the 9th solar masses per cubic parsec near the event horizon. Such conditions disrupt atomic structures and cause matter to behave in ways that challenge conventional understanding. The rotation also contributes to the emission of powerful gamma-ray bursts, which last for less than 2 seconds, but release more energy than the Sun will in its entire lifetime. Gamma-ray bursts from supermassive black holes like Sagittarius A have been observed to last for less than 2 seconds, but release more energy than the Sun will in its entire lifetime. These brief, intense events are a testament to the extreme forces at play near these cosmic giants. The Milky Way rotates once every 250 million years around its central black hole, with each rotation bringing new matter into proximity with Sagittarius A, potentially leading to further star formation and black hole growth. This cyclical process underscores the dynamic nature of our galaxy's core. The discovery of the cosmic microwave background radiation in 1964 provides evidence for the Big Bang theory, suggesting that our universe was once a hot, dense point. This ancient radiation, which fills the entire observable universe, offers clues about the early conditions of the cosmos. The extreme temperatures and pressures near Sagittarius A are reminiscent of these primordial conditions, offering a glimpse into the universe's infancy. Understanding these processes helps us comprehend how the universe evolved from its initial state to the complex structure we observe today. The slow transformation of cosmic structures as they converge on Sagittarius A is a process that unfolds over eons, with subtle yet profound effects on the fabric of our galaxy. At its core, this supermassive black hole exerts an influence that reaches far beyond its immediate vicinity, shaping not just individual stars, but entire galactic arms. The accretion disk surrounding Sagittarius A is a thin plane of matter spiraling toward the event horizon, where temperatures can reach up to 1 billion Kelvin due to friction. This extreme heat contrasts with the cold void that surrounds it, creating an environment where new stars struggle to form. As material approaches the black hole, its journey becomes increasingly complex. Stars caught in this gravitational pull experience intense tidal forces, stretching them into elongated shapes known as tidal tails. These tails can stretch for thousands of light years, marking the path of stellar debris as it is drawn toward the galactic center. The process of stars being torn apart and reformed near Sagittarius A highlights the dynamic nature of cosmic structures in this region. Despite these extreme conditions, some stars manage to form within or near the accretion disk, born from the same material destined for oblivion. The gravitational influence of Sagittarius A extends far beyond its immediate surroundings, shaping the distribution of matter throughout the entire galaxy. Stars at the edge of the Milky Way feel this pull as they trace out their orbits, creating the spiral arms that give our galaxy its distinctive shape. This connection between the galactic center and regions up to 50,000 light-years away underscores how events near Sagittarius A resonate across the breadth of the galaxy. The black hole's gravitational field distorts space itself, causing stars to orbit in intricate patterns dictated by its presence. The accretion disk around Sagittarius A is not just a passive structure, but an active participant in the galactic ecosystem. As matter spirals inward, it collides and merges, releasing vast amounts of energy in the form of radiation. This process illuminates the region near the black hole, making it one of the brightest parts of our galaxy. The light emitted from this area can be detected by telescopes on Earth, providing valuable insights into the dynamics at play. Despite its brightness, the accretion disk remains invisible to human eyes due to the extreme gravitational forces that prevent photons from escaping. The transformation of cosmic structures near Sagittarius A is a process that has been ongoing for billions of years and will continue long into the future. As stars are drawn closer to the black hole, their orbits become more chaotic, leading to collisions and mergers that reshape the galactic core. These events contribute to the formation of new celestial bodies, while also dispersing matter across vast distances. The process is both destructive and creative, highlighting the cyclical nature of cosmic evolution. Over time, this region will continue to influence the structure and behavior of our galaxy. Intriguingly, the conditions near Sagittarius A provide a unique laboratory for studying extreme physics. The intense gravitational forces and temperatures create an environment where matter behaves in ways that challenge conventional understanding. For instance, the density near the black hole can reach up to 4 billion solar masses per cubic parsec, creating pressures that disrupt atomic structures. This region serves as a natural experiment, offering insights into phenomena that are otherwise difficult to study on Earth. Despite these extreme conditions, Sagittarius A remains a focal point for scientific inquiry, drawing researchers and telescopes from around the world. Near the event horizon of Sagittarius A, time behaves in ways that challenge our understanding, stretching and compressing as if on a cosmic rubber band. For an observer near this boundary, every second can feel like centuries due to extreme time dilation effects. The temperature here reaches up to 1 billion Kelvin, driven by friction within the accretion disk. This heat is so intense it would vaporize any matter that approached too closely. Gamma-ray bursts from supermassive black holes like Sagittarius A are some of the most powerful events in the universe, lasting for less than 2 seconds, but releasing more energy than the Sun will produce in its entire lifetime. These bursts occur when a black hole consumes large amounts of matter at once, creating shock waves that ripple through space-time itself. Though sound cannot travel beyond the event horizon, these gamma-ray bursts serve as cosmic messengers, informing distant observers of the intense activity near the black hole. The density near Sagittarius A reaches an extraordinary 4 × 10⁹ solar masses per cubic parsec, creating gravitational forces that warp time by slowing it to a crawl. This pressure and temperature environment is beyond anything experienced on Earth, with temperatures far exceeding those found in any laboratory setting. The extreme conditions here not only stretch time, but also warp it, making events seem to unfold at different rates for observers at varying distances from the black hole. The accretion disk surrounding Sagittarius A is a swirling maelstrom of superheated matter and radiation, reaching temperatures up to 1 billion Kelvin due to friction. This intense heat disrupts atomic structures, transforming familiar elements into an ionized plasma. The environment here defies the usual rules governing sound propagation. Even if sound waves could form in such conditions, they would be absorbed instantaneously by the energetic plasma. At a distance of 26,000 light-years from Earth, Sagittarius A is not merely a point in space, but a gravitational nexus where matter and energy converge in profound ways. The supermassive black hole at our galaxy's heart exerts an influence that reaches far beyond its immediate vicinity, shaping the very fabric of spacetime around it. This influence extends to distant regions of the universe through subtle ripples in spacetime, connecting Sagittarius A with cosmic structures billions of light-years away. The gamma-ray bursts from Sagittarius A provide fleeting glimpses into the extreme conditions near the black hole's event horizon. These bursts, lasting mere fractions of a second, are among the most energetic events in the universe. They release more energy than our sun will produce over its entire lifetime, yet they occur so rapidly that any sound-like disturbances would be imperceptible to human ears. Surprisingly, these gamma-ray bursts can also create temporary ripples in spacetime that propagate outward at nearly the speed of light, briefly warping space for distant observers. In this environment, matter cannot exist in its normal state due to extreme temperatures and pressures that disrupt atomic structures. The density near Sagittarius A is so high that it challenges our understanding of physics. At the core of a supermassive black hole, time dilation effects prevent any object from reaching or passing through the singularity within finite proper time, as observed by distant observers. This phenomenon creates an auditory distortion where sound waves would be stretched and compressed in ways unimaginable to human ears. The stretching and compressing of time near Sagittarius A create a unique form of auditory distortion, even though sound itself cannot propagate in the vacuum of space. For an observer approaching the event horizon, this temporal warping would manifest as a series of abrupt pitch changes and rhythmic distortions, akin to hearing music played at varying speeds on a phonograph. The closer one gets to the black hole, the more pronounced these effects become, until time itself seems to stutter or skip forward in fits and starts. This phenomenon is not just a theoretical curiosity, but a direct consequence of Einstein's theory of general relativity, where gravity warps both space and time. The gamma-ray bursts from Sagittarius A provide fleeting glimpses into the extreme conditions near the black hole's event horizon. These bursts, lasting mere fractions of a second, are among the most energetic events in the universe. They release more energy than our sun will produce over its entire lifetime, yet they occur so rapidly that any sound-like disturbances would be imperceptible to human ears. The sheer intensity of these bursts underscores the violent nature of the black hole's environment, where matter is torn apart and reconfigured on scales far beyond what we can imagine. The extreme conditions near Sagittarius A challenge our understanding of physics and push the boundaries of what we can observe or even imagine. Time dilation effects create an auditory environment where time itself. In ancient myths, the center of the universe was often seen as a divine point of creation and power, a place where gods resided and fate was determined. Today, we know that our galaxy's heart lies 26,000 light-years away from Earth, at Sagittarius A, a supermassive black hole with a mass equivalent to about 4 million suns. This cosmic giant is not just a point in space, but a gravitational nexus where matter and energy converge in profound ways. The temperature near the event horizon of Sagittarius A can reach up to 1 billion Kelvin due to accretion disk friction, creating an environment so extreme that it challenges our understanding of physics. Yet, this inferno contrasts with the cold spot nearby, which defies thermal expectations by maintaining temperatures far below what would be expected in such a hot region. This paradox highlights how nature can confound human intuition and preconceived notions. Our galaxy rotates around Sagittarius A once every 250 million years, an orbital period that dwarfs the lifespan of any individual star or planet within it. The sheer scale of this motion underscores the vast timescales at play in our universe, a reminder that human lifespans are but fleeting moments in cosmic history. This cyclical movement is akin to the ancient belief in celestial cycles influencing earthly events. The density near Sagittarius A can reach up to 4 × 10⁹ solar masses per cubic parsec, creating extreme gravitational forces that warp space and time. These conditions are so intense they prevent any object from reaching or passing through the singularity within finite proper time, as observed by distant observers. This phenomenon echoes ancient myths where divine beings were thought to reside in unreachable realms beyond human comprehension. Gamma-ray bursts from supermassive black holes like Sagittarius A have been observed to last for less than 2 seconds, but release more energy than the Sun will in its entire lifetime. These brief, intense events are a testament to the immense power contained within these cosmic entities, challenging our understanding of how such phenomena can occur. The fleeting nature of these bursts contrasts sharply with the enduring presence of Sagittarius A, which has been influencing the Milky Way for billions of years. The cosmic microwave background radiation discovered by Penzias and Wilson in 1964 provides evidence that our universe was once a hot, dense point from which everything expanded. This discovery connects the ancient myths about celestial centers with the scientific understanding of how our universe began. The remnants of this primordial fireball continue to permeate space, serving as a cosmic echo of the Big Bang and reminding us of the profound interconnectedness of all things in the cosmos. The ancient Greeks believed that the center of the universe held the axis mundi, a point where heaven and earth met, thought to be the source of divine power and cosmic order. This notion finds an eerie parallel in modern astrophysics with Sagittarius A, which not only anchors our galaxy, but also influences its structure and evolution. The supermassive black hole's gravitational pull shapes the orbits of stars and gas clouds, much like a celestial architect guiding the construction of the universe. Yet, unlike the static axis mundi of myth, Sagittarius A is dynamic, feeding on matter and energy that swirl into its maw, continually reshaping the fabric of space around it. In many ancient cultures, the central point was seen as a portal to the divine or an intersection between different realms. This idea resonates with contemporary theories about black holes acting as gateways to other dimensions or even entire universes. While these concepts remain speculative in science, they highlight how human imagination and scientific inquiry both grapple with the mysteries of the cosmos. The myths may have been metaphorical, but the physical processes at play near Sagittarius A are no less awe-inspiring, revealing a universe that is as grand and intricate as any divine creation imagined by ancient peoples. The discovery of Sagittarius A has led to new insights into the formation and evolution of galaxies. Just as myths often explain the origins of natural phenomena, modern astronomy seeks to unravel the cosmic history written in the stars. The supermassive black hole at our galaxy's heart is a relic from the early universe, formed during epochs when conditions were vastly different from today. It stands as a sentinel, bearing witness to billions of years of cosmic evolution, a living monument to the forces that shaped not just our galaxy, but countless others across the cosmos. The connection between ancient myths and modern astrophysics extends beyond mere coincidence. Both offer narratives that seek to explain the unknown, whether through storytelling or scientific observation. The process by which light behaves differently around Sagittarius A creates halos visible from distant galaxies, offering a unique perspective on our cosmic neighborhood. These halos are formed when intense gravitational forces bend and focus light in extraordinary ways. Near the event horizon of this supermassive black hole, temperatures reach up to 1 billion Kelvin due to accretion disk friction, causing photons to behave erratically. This extreme environment distorts light paths, creating patterns that can be observed from Earth despite the 26,000 light-year distance. Yet, these halos are not just spectacles. They serve as cosmic lenses, revealing distant galaxies and phenomena otherwise obscured by intergalactic dust. Light bending around Sagittarius A is a phenomenon known as gravitational lensing, where massive objects curve spacetime itself. This effect magnifies and distorts the light from background sources, creating multiple images of the same object. For an observer on Earth, this means seeing not just one galaxy but several versions of it, each slightly different due to varying paths through the curved space. The precision with which these halos can be observed allows astronomers to map the distribution of dark matter in our galaxy and beyond. This mapping reveals that dark matter forms a halo around Sagittarius A, contributing to its gravitational influence without emitting any detectable light. The temperature near Sagittarius A reaches up to 1 billion Kelvin, creating conditions where even light behaves unpredictably. In these extreme environments, the photon's paths are not just bent, but also stretched and compressed by time dilation effects. This means that for an observer far from this region, the light might appear as if it is moving slower or faster than expected. These distortions provide a window into the physics of black holes, offering insights into how gravity can warp space and time to such an extent that even light cannot escape unaltered. The halos act like cosmic fingerprints, each unique in its pattern and intensity, revealing not just the presence of Sagittarius A, but also the intricate dance of matter and energy around it. In addition, these conditions create a phenomenon known as gravitational redshift, where photons lose energy as they climb out of the black hole's gravitational well, shifting their wavelength to longer frequencies. Gamma-ray bursts from supermassive black holes like Sagittarius A have been observed to last for less than 2 seconds, yet release more energy than the Sun will in its entire lifetime. These brief, intense emissions are a result of matter falling into the black hole at relativistic speeds. As this material spirals inward, it heats up and emits radiation across various wavelengths, including gamma rays. The halos around Sagittarius A capture these bursts, amplifying their intensity and making them visible even from such great distances. This phenomenon underscores the paradoxical nature of black holes. While they are often seen as cosmic vacuum cleaners, they also act as some of the most powerful engines in the universe, capable of producing more energy than all stars combined. The halos around Sagittarius A not only reveal distant galaxies, but also provide a glimpse into our own galaxy's past. By observing these light distortions, astronomers can trace back the history of star formation and galactic evolution within the Milky Way. The patterns in the halos offer clues about how our galaxy formed and evolved over billions of years. For instance, the presence of certain elements in the distorted light can indicate periods of intense star birth or supernova activity. This cosmic archaeology allows us to understand not just what Sagittarius A is doing now, but also its role in shaping the Milky Way's structure since it first formed 13.6 billion years ago. Interestingly, these halos occasionally reveal unexpected phenomena, such as the sudden appearance of new stars forming within the accretion disk itself, a process that challenges our understanding of star formation under extreme gravitational conditions. Intriguingly, these halos are not static. They evolve over time as matter and energy interact with Sagittarius A. The accretion disk around the black hole is constantly changing, influenced by incoming gas clouds, stellar winds, and even other black holes in distant galaxies. As this material spirals inward, it heats up and emits radiation that shapes the halo's appearance. This dynamic interaction means that what we observe today will look different tomorrow, offering a continually shifting window into the universe's most extreme environment. The halos around Sagittarius A are thus not just passive reflections of cosmic light, but active participants in the ongoing story of our galaxy's evolution. Cosmic strings crossed paths here, marking a moment in time that predates our understanding of space and time as we know them today. This intersection occurred approximately 13.8 billion years ago, birthing what scientists refer to as the initial singularity, the densest point in the universe's history. The energy released during this collapse was immense, contributing significantly to the early expansion and structure formation of the cosmos. At this moment, temperatures and densities were far beyond anything we can replicate in laboratories on Earth. Imagine standing near the event horizon of Sagittarius A, where time stretches infinitely for an observer outside, but ceases to exist inside. The extreme gravitational forces would distort space-time so profoundly that light itself cannot escape. For distant observers, this area appears as a black void, yet within lies an environment where matter and energy are compressed to such extremes that they defy conventional laws. At the event horizon, time slows down to a crawl for objects approaching it at near-light speeds, eventually stopping entirely for anything that crosses the boundary. The journey from cosmic strings crossing paths to the formation of Sagittarius A took billions of years. During this time, matter coalesced into stars and galaxies, each playing its part in shaping the universe's evolution. The supermassive black hole at our galaxy's heart is not an isolated phenomenon, but a product of cosmic processes that have been unfolding for almost 14 billion years. These processes include the formation of nebulae, the birth of stars, and the eventual collapse of massive stellar cores into black holes. However, one unexpected fact about Sagittarius A is its relative calmness compared to other supermassive black holes. Despite being at the center of our galaxy, it consumes matter at a remarkably slow rate, suggesting that it may have been dormant for long periods in the past. In the vicinity of Sagittarius A, temperatures near the event horizon can reach up to 1 billion Kelvin due to accretion disk friction. This heat is generated as matter spirals inward toward the black hole, colliding with other particles at incredible speeds. The energy released in this process is equivalent to thousands of supernovae exploding simultaneously. Yet, paradoxically, there exists a cold spot nearby that defies all thermal expectations, maintaining temperatures far below what would be expected given its proximity to such intense heat sources. At the core of Sagittarius A, matter cannot exist in its normal state due to extreme temperatures and pressures that disrupt atomic structures. The density near this supermassive black hole can reach up to 4 × 10⁹ solar masses per cubic parsec, creating gravitational forces so strong they warp spacetime itself. This environment is far removed from the stable conditions of Earth's surface, where matter exists in a predictable form and follows well-understood physical laws. Gamma-ray bursts from supermassive black holes like Sagittarius A have been observed to last for less than 2 seconds, but release more energy than the Sun will in its entire lifetime. These brief yet powerful events are thought to be caused by the collapse of massive stars or collisions between neutron stars, leading to the formation of new black holes. The energy released during these bursts can ionize vast regions of interstellar space, influencing star formation and galaxy evolution across cosmic distances. The wormhole could play a role in these bursts by acting as an escape route for high-energy particles and radiation, preventing them from being trapped indefinitely near the event horizon. This dynamic interplay between the black hole, its accretion disk, and the mysterious tunnel offers a glimpse into the complex processes at work in this cosmic powerhouse. The energy released during these events could have far-reaching consequences, affecting star formation and galactic evolution across vast distances. In the heart of our galaxy's supermassive black hole, where conditions are so extreme that matter cannot exist in its normal state due to temperatures reaching 1 billion Kelvin and pressures beyond imagination, we find an unexpected neighbor, a wormhole linking this universe's core to another dimension's outskirts. This cosmic connection defies conventional understanding by providing a pathway between two vastly different realms. The initial coordinates discovered through the fury of solar flares now take on new meaning as they point not only to Sagittarius A, but also to an intersection with another reality. In this final revelation, we see how the universe's most extreme conditions can birth phenomena that challenge and expand our comprehension of space, time, and existence itself. At the core of Sagittarius A, the density reaches up to 4 × 10⁹ solar masses per cubic parsec, creating gravitational forces so intense they warp space-time in ways we cannot fully grasp. This extreme environment is not just a point of convergence for matter, but also a site where quantum effects become pronounced. For instance, particles can momentarily appear and disappear due to the high energy density, a phenomenon known as vacuum fluctuation. These fluctuations are fleeting yet significant, offering insights into the fundamental nature of reality at such scales. Gamma-ray bursts from supermassive black holes like Sagittarius A have been observed to last for less than 2 seconds, but release more energy than the Sun will in its entire lifetime. This brief burst of energy is a result of matter falling into the black hole and being compressed to extreme densities, causing violent explosions that emit radiation across the electromagnetic spectrum. The sheer intensity of these bursts can be compared to the power output of billions of suns concentrated into mere moments, highlighting the extraordinary forces at play in such environments. The cosmic microwave background radiation discovered by Penzias and Wilson in 1964 provides evidence that our universe was once a hot, dense point. This discovery reveals that the conditions near Sagittarius A are not unique to our galaxy, but echo the state of the early universe. The extreme heat and density found near the black hole's event horizon mirror the conditions just after the Big Bang, suggesting that studying these regions can offer insights into the origins of everything. Near the center of our galaxy, the rotation of stars around Sagittarius A provides a natural clock for cosmic events. These orbits take approximately 250 million years to complete, a timescale that dwarfs human lifespans but is crucial for understanding galactic evolution. As we observe these stellar movements, it becomes clear that the center of our galaxy is not just a point in space, but a dynamic system where time unfolds at its own pace, shaping the fate of stars and galaxies alike. This slow dance of cosmic bodies mirrors the initial image of coordinates birthed from radiation's fury, revealing how deeply connected all parts of the universe truly are. In the heart of a solar flare's fury, where silence birthed coordinates to cosmic secrets, we find ourselves again, gazing into Sagittarius A, the silent sentinel at the center of our galaxy. This journey through the cosmos is coming to an end. Thank you for sharing this quiet adventure with us tonight. If you liked what you heard, consider subscribing and leaving a like. Good night. Chinese letter, Chinese letter, Japanese letter, Chinese letter, Chinese letter, Japanese letter, Japanese letter.